Let's look what thermodynamics can teach us about more complex systems like those of heat pumps and machines. Now, what air-cooled heat pumps or fridges do is that they pump heat from one compartment to another one through applying electrical energy. For the air-cool, we would have a room which should stay at a cold temperature, T cold, and the air conditioning pumps out heat from this room and transfers this heat into the hot surrounding of the outside, which is at temperature T hot. Now, in order to do this, the AC needs electrical energy W. The process that we just described has to obey the first law of thermodynamics, or the conservation of energy. If we look at what flows in and out of the AC, this can be formulated that plus delta QC minus delta QH plus W larger or equal to 0. Further, the process has to obey the second law of thermodynamics, stating that the final entropy will increase. Now, the change of entropy is related to the change of heat. Hence, the change in total entropy is given by minus delta QC divided by TC plus delta QH divided by TH, which has to be larger than 0, from which we can obtain a relation between the ratios of the changes in heat and the relative temperatures of the two compartments. By this, we can now define the efficiency of the machine, eta AC, which is given by how much heat is pumped out of the cold room divided by the amount of energy that we have to put into the AC machine. Now, filling in the above two equations, what we obtain is the final equation of the efficiency of the AC, given by the temperature of the cold room divided by the difference temperature of the hot to the cold room. Now, it's not too surprising if the temperature change between the outside and the inside is too high, this efficiency goes to 0. Now, the same calculation also holds for the heat pump, where we want to pump heat from a cold compartment into a hot room. There, the efficiency of the heat pump, eta HP, is given by the ratio of the amount of heat that is pumped into the hot room divided by the electrical energy. And we again find this is given by the ratio of the temperature in the hot room divided by the difference temperature between inside and outside. Again, going to 0 if the difference is too high. Now, in the second example, we are concerned with machines. In a typical machine like this steam engine, what you do is you take two compartments, a hot compartment and a cold compartment, and use the flow of heat in order to transfer this heat into useful mechanical or electrical energy. Again, we have to obey the conservation of energy, leading to plus delta QH minus delta QC minus W is now small or equal to 0. And the second law of thermodynamics, which requires entropy to increase. Now, doing the same mathematics as in the earlier example, we now obtain the efficiency of thermodynamic machines. Eta machine is smaller than 1 minus Tc divided by Th. Hence, the efficiency is always smaller than 1, and in particular, if the two heat baths have the same temperature, it approaches 0. The efficiency of thermodynamic machines increases with difference temperature between the hot and the cold compartment. These few examples demonstrate the power of thermodynamics. Even very complex systems, like those of thermodynamic machines, can be easily explained, and it can be understood why efficiency of thermodynamic machines is limited and what are the parameters that limit use.